So this is putting exponential functions all together. We're going to be moving from one form on the web of representations. If I have a situation, I'm asking you to find the graph and the table and the equation. I've used the same examples that I have on your paper, so you can go ahead and follow along. It doesn't look exactly the same, but the examples are the same. First, we're going to do is talk about finding multipliers. And if you have a multiplier in a table and you can tell that it's not adding by the same number, so it's not arithmetic, then you're going to start to look to see if the multiplier is consistent and it's exponential. So to find the multiplier, we're going to divide term 1 by term 0, or times term 2 by term 1. And we get 1.3 and 1.3. So this is a multiplier of 1.3. And sometimes when you're dealing with real data, these multipliers might not be perfect. It might be 1.31 or 1.294. If they're, because we're rounding to the nearest person, it might be a little off, but you're looking for a good approximation of a multiplier. This one's exactly 1.3, which we want to talk about what that means in terms of percent growth. This one is growing by 30% at a time. The 1 stands for the 100%, so this has to do with the original amount, and the 0.3 stands for the 30% more. So a 1.3 means a 30% increase. If you're going from a situation, you have to think about whether you're talking about an increase or a decrease, and that's the first thing you're doing. And I had it set up in a table for you on your work, but that's the process you want to do, looking through. It's like, I've got the number of infected people, it's increasing, so we're going to go ahead and take the original 100% and add it to the 30% that it's increasing by each day. So we get a total of 130% of what was there before, the original and the new 30%. So that works out to be a multiplier in decimal form of 1.3 or 1.30. Both are correct. Now if the population's dropping, then we're talking about a subtraction. We're going to take 100%, the original, and we're going to drop it by 30% a year. So that means we're going to deal with 70% left. So our multiplier would be in decimal form 0.7 or 0.70. So you got to pay attention to, is it growing? Is it shrinking? And then if it's growing, you're going to add 100% to the percent increase. If it's shrinking, you're going to drop by subtracting. So here are a couple of situations. This to the left, you're talking about when you are going to add 100% to the percent. When there's population growth or compound interest, that means you're getting money on your money, a price markup or a tax or a tip, and you want the total price with the markup, and you want the total amount you're going to spend, including the original and the tax or tip, then you're going to be looking at a multiplier of 100 plus the percent. If you're talking about a decay, that means you're going to multiply by a number less than 1 over and over and over again. You're going to see a downward facing curve. So a population decline, radioactive decay, when isotopes lose parts and they get smaller and smaller, discount, or a percent drop in the stock market. The ones that have stars, they're not really exponential growth or exponential decay, because you're really only making that calculation that one time, but the multipliers work the same way. Exponential growth would require multiplying by the same percentage over and over and over again for it to be considered exponential. Growth, getting bigger; decay, getting smaller. Growth, the multiplier is bigger than 1. Decay, the multiplier is less than 1, but bigger than 0. here we have a population, here we have the graph, and what I decided is we were going to be looking at a population of monkeys and how they are dropping in population. So I know my starting amount is 16,000, and my first year it dropped to 14,000. So this is a situation, we can tell by the curve that it's exponential, plus I told you it was exponential. And so here we have an opportunity to use that division to find the multiplier, term 1 by term 0. So we're going to go ahead and divide 14,000 divided by 16,000. And we know it's shrinking down, so our multiplier should be less than 1, and we do the calculation, we get 0.875. When we continue to do that multiplication, it's going to go down, continuing to go down, so 14,000 times 0.875 works out to be 12. Oops, I need my blue back. 12,250, and then again it'll be 10,000, and my calculator says 10,718.75, but since I'm dealing with monkeys, I'm going to round to the nearest monkey, so it's 10,719. Whoops, it's not working. Why aren't you working? It won't write. There we go. 719. Now the situation I chose was to talk about a population drop for monkeys, but no matter what situation you figured out, decided upon, we're still having the same starting population of 16,000 or $16,000 or 16,000 people, and it's dropping, so there's 87.5% left, and X is going to stand for the number of years. Since 87.5% are left, that means they are dropping at a 12.5% rate. Here we have an equation, and we know that this 3,000 is our starting amount. I've decided to let the situation be money compounded annually. You don't have to do it that way. So the starting amount is always going to be my zero term. So I have $3,000 in the bank, and I'm going to grow at 4% compounded. The 100 is this one, the original 100%, and then the 4% more that I have each time. So after the first year, second year, and third year, so I have 3,000 times 1.04, which gives me 3,120, and times 1.04 again, and I have 3244.8, which in money is 80 cents. One more time, I get 3374.592, and I've got to think about what that means in terms of money. So looking at that, here's where the money stops, right there, and there's not enough there for us to round up, so it'd be 3374.59. So I can go ahead and write it as 3374.59, and the machine will not let me do that, so I'm gonna just cross it off with my pen. So if you have an equation, you recognize that the first part is your starting amount, and then the multiplier is going to tell you that what kind of growth it is. And if it's plus, what's 1.04, it's 4% higher growth, and if it's less, then you're going to do 100 minus to figure out what kind of growth you're talking about. So now we're dealing with a situation, and that's where you have to think about the process of what is going on. Founders, by the way, are people that are the beginning people in an organization. In this case, it's a company. We talk about our founding fathers when we talk about the people who started our government. So in this case, we have 10 founders, and so that goes into our zero term. And then this grows at a rate of 20%. Growing means plus, so we're going to go ahead and take our original 100%, which 100% in this case is 10, and we're going to add the 30. Of course, you don't have to, oh, it's not 30, it's 20. Sorry, I'm thinking about something earlier. We're going to add our 20, and so we're going to get 120% in decimal form, which is 1.2 or 1.20. Now, when I multiply by 1.2 or 1.20, I'm going to get 12 the first time, and that's 12 people. When I multiply it times 1.2 the second time, I get 14.4. Now 14.4 is not an actual person's worth, so we're going to go ahead and leave it at 14 people. We're going to round to the nearest person. Next time we get 17.28, same thing, we're going to keep it at 17. We're going to round to the nearest person. Times 1.2 again, we get 20.736, that's closer to a whole nother person, so we're going to round to 21. So when you're dealing with these decimals, you want to make sure your answers make sense. If I were doing a good sketch, I have enough data to do this, but for my purposes, since it's really small, I'm going to go ahead and start at 10 and show that it's growing exponentially like that. That would be a reasonable sketch, but when I ask for one off of a table, I expect it to be a accurate sketch based on the data. Last one, once again, we have a table, and we need to find the multiplier, and we find the multiplier by dividing backwards. So 54.1 divided by 67.6. When we do that division, we get a multiplier of 0.8. So now we have part of what we need to write the equation, but not everything. So we're going to go ahead and have to, since we are multiplying by 0.8 going forward, then we can divide by 0.8 going backwards. So 84.5 divided by 0.8 gives us 105.625, and since they rounded to the nearest tenth, I'm going to round to the nearest tenth, so I'm going to get 105.6, and then I'm going to divide by 0.8 again, and I'm going to get 132. So now I have what I need to write the equation. I have my zero term, my initial amount. I have my multiplier of 0.8 to the x power. And actually this is an example of a sequence, and we could use sequence notation because each bounce is its own thing, and we can't talk about a half of a bounce. So this is a perfect example of a sequence. So what's going on here? The situation, this is a ball dropped at 132 centimeters that loses 20% of its height each time. So since it's 0.8 of a multiplier, that means 100 minus 80%, remember that's what that is in percent form, that means we have 20% is what's being dropped each time. So it's losing 20%, it keeps 80% of its height until it stops working. So you need to be able to go from all the different representations, finding a multiplier from words, finding a multiplier from a table, putting it in the equation, being able to generate the fifth term or the second term or the whatever, reading an equation. I know you can do all this. Practice what you've got, and we'll see what questions you have tomorrow.